Hello everyone, my name is Sam, and today I'm going to be talking with you about the second law of thermodynamics and the tendency for the universe to want to increase in entropy, as exemplified by my kitchen sink. So what is entropy exactly? Well, in my favorite textbook entitled Elements of Physical Chemistry, the 6th edition of course, by Atkins and DePaula, there is an excellent definition that I would like to show you. Now, this definition is not specifically for entropy, but it kind of gets at what I would like to talk about. And it says, the apparent driving force of spontaneous change is the tendency of energy to disperse and matter to become disordered. Now, this is not an explicit definition of what entropy is, but it is kind of explaining what it's all about. And I know when you see spontaneity, you're probably thinking of Gibbs free energy. Now let's just draw a little equation for that, if I can steady my hand a little bit. So we have Gibbs free energy, delta G, equals change in enthalpy, denoted delta H. I will not be going into enthalpy too much. Someone else can discuss that in their video. And then we have minus capital T, that of course is temperature in Kelvin, delta S. And this delta S, that is what we're talking about. That is change in enthalpy. As you can see, there is a negative sign in front of the T delta S. And if we can remember, spontaneous, that's not how you spell it. Well, you know what I'm talking about. So, delta G, a spontaneous reaction occurs when delta G is negative, that is to say less than 0. And as you can see from the above equation, delta G can become negative. Like I said, we're ignoring enthalpy. Delta G can become negative if delta S is positive, thereby giving a negative value to T delta S. That just goes to show that when entropy increases, a reaction can become more spontaneous in terms of Gibbs free energy. Now that we have a little bit better understanding as to what specifically entropy is, the question becomes, what exactly is the second law of thermodynamics? Well, let me tell you. The second law of thermodynamics states that the entropy of the universe tends to increase. Now, what is the universe? Now, that might seem like a strange question, but in chemistry, it's actually somewhat important. So the universe, oh, spelled that one right, is equal to a system plus everything that is not the system, that is to say the surroundings. So that is what the universe is. System plus the surroundings. Typically in chemistry, we forget to consider the surroundings because we're more concerned with the system. But when it comes to entropy, it's important to note the distinction between the system and the surroundings and the role they play in contributing to the ultimate universe. Now that we know what the universe is, and now that we know what entropy is, let's just talk about how entropy is related to the universe in terms of the second law of thermodynamics. So the second law of thermodynamics, like I stated, is the tendency for the universe to increase in entropy. And if we can recall from this equation that I completely massacred, the universe is the summation of the system that we're concerned with as well as the surroundings. So, universe, I'll just rewrite this real quick, add a couple seconds onto my video. System, oop, there's an E in there, plus surroundings. So this is actually more important than it would at first appear, because even if we have a system that is decreasing in entropy, for example, a gas being turned into a liquid or a solid, where entropy is decreasing, the universe still would be increasing in entropy because of the surroundings. So the decrease in entropy attributed to by the system is counteracted by an increase in entropy of the surroundings. And we will see this in a couple examples that I will show you very shortly. Boiling water is an excellent example of the second law of thermodynamics. As the water changes from the liquid phase to the gas phase with the input of energy, entropy increases. Bam! Now, as you can see, my reaction mixture is cooling in an ice vat and therefore decreasing in temperature. This ultimately results in a decrease in entropy for my system. Nonetheless, by cooling my mixture, the ice vat is in turn heating up due to the heat exchange between my mixture and the vat. Therefore, even though the entropy of my system is decreasing, the entropy of the surroundings is increasing, so the universe is happy. Alright, so check this out. Right here we have my delicious breakfast, 4 hard-boiled eggs. As you can see, they're currently in the process of being cooked. Okay, I know what you're going to say. You're going to say, Sam, that looks like a delicious breakfast. And yes, that is a very important piece of information to take note of. But more importantly, you're going to say, whoa, Sam, hold up. What do eggs have to do with the second law of thermodynamics? Well, listen up and I'll drop some knowledge on you. As you can imagine, when I first put my eggs in the pot, they were more or less liquid on the inside. And now that they're being heated, the insides are beginning to solidify. And as we all know, this type of phase change can be associated with a decrease in entropy. Now let me guess what you're going to say. You're going to say, but Sam, I thought you said the entropy of the universe tended to increase, not decrease. Well, hold up, fool, I wasn't finished. If you look a little closer, you'll notice that the surroundings of my system are in fact increasing in entropy. For example, the water that is being used to cook the eggs is heating up and vaporizing. Let's see if we can get a live action shot of that. Well, I assure you it's happening. Thereby exemplifying the surroundings entropy increase. Additionally, if I had invited you over for breakfast, you could see for yourself that the stove is getting very hot from me cooking these eggs. Ooh! Ouch! You'll just have to take my word on it. This heat flow to the surroundings is also evidence of the increase in entropy. Finally, if you take note of the fact that my stove is a gas stove, let's see if we can get a glimpse of that. Oh yeah, there we are. And if you keep in mind that the flame it produces is the result of a combustion reaction, which in many cases, but not all cases, results in an entropy increase. So as you can see, the second law of thermodynamics is all around us, even in our breakfast. Now when you start thinking about entropy and the second law of thermodynamics, you probably envision a whole bunch of fancy definitions and sophisticated math equations. But if you really want to understand how the entropy of the universe tends to increase, let me give you a quick tour of my house. We're going in. First and foremost, what is that? Who does that belong to? Alright, we're going into the kitchen. Not much entropy here. There's a little more over here. Let's see. Kitchen's actually looking pretty decent right now. But wait. Dang! That's where all the entropy is. Check that out. Look at the dining room table. Someone left a whole bunch of soda cans over there. Let's see. Oh, whoa. Check out all this mail. Now that is what I'm talking about, entropy. If I had to take a guess, I would say Boltzmann is probably rolling around in his grave right now. Well, I think that's all you need to see of my humble abode. Oh my goodness, I completely forgot about this room. Alright, well, there's also quite a bit of entropy in here. But I would also like to take note that I've been told that the ethanol bake-off is going to be held here, so you all might want to invest in a hazmat suit. Alright everyone, that concludes my video concerning the second law of thermodynamics, so I would like to thank you for watching, Not only I thank you, but ASAP Rocky would also thank you. Good night.